So in this video, we're going to take a look at these cyclohexanes and draw both chair conformations. So the first thing I want to do is identify the relationship between the two functional groups or the two substituents I have on my six-numbered ring. So in this case, again, the numbering doesn't really matter exactly how you number it, but the relative positions of the two groups is the most important. So I'm going to choose this as my carbon 1, 2, 3, and 4. So again, I have a 1-4 relationship between my methyl group, which is in the up position. So again, based on the fact that we have this wedge, it's going to be above the chair. And so 1 is up. Also, the 4 position is also up. And since they're both going in the same direction, we would say that these two substituents are cis to each other. So they have a cis relationship. So let's go ahead and draw the chair. So I'm going to start by drawing the chair that has the carbons kind of leaning to the right. So I'm going to draw the chair backbone here. Again, drawing parallel lines initially, and then another set of parallel lines. If my stylus works. Another set of parallel lines as best I can. So parallel lines here. It's not the best chair, but parallel line. It's a little bit more of a bow tie. I'll try to do better on the next chair. So if this is carbon 1, this is carbon 2, and carbon 3, and carbon 4. And again, I can number these however I want to, but I typically tend to choose the one that is up on the far right-hand side as my carbon 1. The reason why I do that is I know that this position here always has the axial up. So this is going to be axial up, and since this is in the up position here, that is where my CH3 is going to be. So my CH3 is going to be at this position here. Okay. So ultimately, if I can establish this bond here, then I can draw all the corresponding bonds for the rest of the molecule. And the way that I do that is I know that I'm going to be alternating in the axial position up and down. So on adjacent atoms, so carbon 2, and I'm going to finish this, carbon 5 and carbon 6, I know that my axial position is going to be going down. So it's going to be axial down at carbon 2, and behind here it's going to be axial down at carbon 6. Those are hydrogens at that position. And then alternating at carbon 3 and carbon 5, since I'm axial down at 2 and 6, it's going to be axial up at carbon 3 and axial up at carbon 5. From there, carbon 4 has to be axial down, and that's where my hydrogen is. And that's important because ultimately that is where my phenyl group is going to be. And again, the phenyl group looks like this. It's basically a benzene ring. It's a shorthand for this benzene ring here. And since I've already drawn the down position at this 4, again, since I have this wedge in the up position, my phenyl group is going to be equatorial. So again, it's going to be parallel to essentially the bond between 2 and 3 and 5 and 6. So the equatorial up position is going to look like this. So pH right there. Okay, so this is one of my chairs. At least I've drawn the important bonds here. And again, in here, I have established the relative positions. Now what I'm going to look for are my 1,3 diaxial interactions, which are making my chair less stable. So my two substituents that I have are my methyl group and my phenyl group. And my methyl group is the only one that is in the axial position. So that's the only one that can do those 1,3 diaxial interactions. And they're going to be interacting with the axial positions that are also up. So as we've drawn here, the hydrogen at carbon 3 and the hydrogen at carbon 5. So here are my two 1,3 diaxial interactions. So from a quantitative perspective, I want to identify the number of 1,3 diaxial interactions that I have and the type. So the way that I would label this is I have two 1,3 diaxial interactions between a hydrogen and a methyl group. So those are sort of my destabilizing interactions that are occurring in this particular chair. Now what I want to do is the chair flip. And in order to do the chair flip, I'm going to draw the carbons sort of angling in the opposite direction. Now it looks like the carbons are sort of leaning to the left. So I'm going to go ahead and draw that. So again, start with parallel lines. I'm going to draw here and connect those here, and then draw here and connect it there. Okay. So again, really what I'm doing in the chair flip is taking this carbon 1 here, pushing it down, and I'm taking carbon 4 and correspondingly pushing it up. Okay, so carbon 1 now becomes this carbon down here, and then carbon 4 becomes this carbon over here. And again, I'm going to put the numbers in here just to kind of help me figure out where the substituents are. So importantly, in the chair flip, everything that was equatorial becomes axial, and everything that is axial becomes equatorial. So my methyl group was axial in my first chair. It's now going to be equatorial in my second chair. However, it was up in my first chair. It's going to stay up in my second chair. So again, it's axial up in first chair. It's going to be equatorial up in the second. And it's going to mirror the bond angle between 5 and 6 and 3 and 2. So it's going to look like this. Okay. Now I'm going to take a look at carbon 4. So carbon 4 has my phenyl group, which was equatorial up in my first chair. It's going to be axial up in my second chair. So again, axial up in my second chair. Okay. Now what I need to do is determine those 1,3 diaxial interactions because those are destabilizing my chair. So what I'm going to focus on are the axial positions that are in the up, because those are the ones that are interacting with my phenyl group. So again, remember it alternates. So I'm axial up in 4, so 3 and 5 are going to be axial down. 2 is going to be axial up, as is 6. And then 1 is going to be axial down. And ultimately, it's this phenyl group that is interacting with the hydrogen in up at axial 6, or up at carbon 6, and the axial up hydrogen at carbon 2. So here again are my 1,3 diaxial interactions. So those are my 1,3 diaxial interactions. So again, what I want to do is label the quantity, the number of them, and the identity. So I have two 1,3 diaxial interactions between, in this case, a hydrogen and a phenyl group. Okay. So now from a qualitative perspective, I have the same number of 1,3 diaxial interactions. Now the difference here is the relative size. So again, thinking about the relative size, I have a methyl group and I have a benzene ring. The benzene ring is going to be larger. So if I have a larger group in that axial position, that's going to make this the less stable chair. So that's the less stable chair, or higher in energy. And correspondingly with the smaller axial substituent, that's going to be the more stable chair. So more stable or lower in energy. Okay, so this is what we would call a qualitative analysis, right? I can differentiate without using numbers that ultimately the chair on the left-hand side with the methyl in the axial position is more stable. I can do a quantitative analysis. I can put numbers to this by using our 1,3 or using our A values. So our A values are essentially the sum of our 1,3 diaxial interactions. So again, another way to think about this is the two 1,3 diaxial interactions between a hydrogen and a methyl are equivalent to 7.1 kilojoules per mole. And again, these A values will be provided for you. You don't need to memorize them. And two 1,3 diaxial interactions between a hydrogen and a phenyl corresponds to 12.6 kilojoules per mole. So if I'm thinking about the relative energy difference between these two, all I'm going to do is take these two numbers and subtract them. So 12.6 minus 7.1 kilojoules per mole. So it's going to be 5.5 kilojoules per mole difference. So if I'm talking about the more stable, it is 5.5 kilojoules per mole less in energy, or the less stable is 5.5 kilojoules per mole higher in energy or less stable.